Welcome back to lesson 13 now of our semester-long videos on circuit analysis. And today we're going to be looking at the source-free RC circuit and separately the source-free RL circuit. Now in the previous two videos we said that the capacitor's job is to store energy in an electric field and the inductor's job is to store energy in a magnetic field. So let's consider the capacitor first, and let's say now it's originally charged, right? So what we could do is we could take a voltage source and we could attach it to the capacitor, and then that charges the capacitor, and then remove the voltage source. That's what makes it initially charged here. So in that sense, since it has energy, it can serve as a voltage source, or a source of energy. So here you see we've got a capacitor and a resistor, but no source, at least not in the traditional sense, no voltage source and no current source. All right, but this thing is, the capacitor is storing energy because it is initially charged. Okay, and we're going to say that the initial voltage across that capacitor, okay, we'll call that V0, or the initial voltage across the capacitor is V0, and recall that the energy then was 1/2 CV squared, and so the initial energy, we'll call that W0. The initial energy that the capacitor is storing is 1/2 CV0 squared, and the initial charge on the capacitor, Q0, is CV0 squared. Okay, and so we're calling this initial, this point in time that's our reference frame, we're calling that time t equals 0. So that's our reference point. And the voltage is right here. Right? There are only two nodes, so there's only one voltage difference right there. Okay, so this voltage from the top node to the bottom node, originally or initially at time t equals 0, is this constant V0. And because there's energy stored there and there's a voltage initially across the resistor, then there's going to be a current flowing through here, even though there is no source. Okay? It's getting the energy from the capacitor. So we'll say, even though we know that there's just one current traveling around that loop, we're not sure of the direction of the current maybe, and so we're just going to say, well, there's going to be a current through the capacitor and there's going to be a current through the resistor, and we know that those are equal and opposite. And so let's write that down, actually. We know from, if you like, Kirchhoff's current law at the top node, we know that IC plus IR, right, the sum of the currents leaving, equals the sum of the currents entering, but there are no currents entering, and so that must be 0. Right? Now, we've also seen from capacitors in lesson 11 that the current through a capacitor is related to the voltage across the capacitor by one of my favorites, C dV dt. The current through the capacitor is C times the derivative of the voltage across. and the voltage across is precisely V. Plus now, we can use Ohm's law to express the current through the resistor. That is V over R. Right? And we are interested in how the voltage is changing as we let time go on. Right? So we want to know what this voltage is. We know what it is initially. It's this constant V0. But it's actually going to change as time goes on, and it's going to change according to this differential equation. Right? It's a differential equation because we have dV dt there, and we're trying to solve for V. Further, this is a first order differential equation because this is a first order derivative. And so this circuit, this RC circuit, we sometimes call a first order circuit. Okay, I'm going to write that down. First order circuit. So a first order circuit is a circuit that can be characterized by a first order differential equation. All right, so we need to solve this differential equation. Well, let me divide everything by C. And I can do that because C is not 0, of course. All right, so now what I can do is use the strategy of separation of variables to solve this. This is the first thing you learn in calculus when you're solving integrals or solving differential equations. So let me get all of the variables with a V on one side of the equation and all of the t variables on the other side of the equation, so-called separation of variables. So this is 1 over V dV equals negative 1 over RC dt. All right, and if I'm after V, then I need to integrate both sides. So the integral of 1 over V dV is the natural log of V, and the integral of negative 1 over RC dt, well, negative 1 over RC, that's a constant. And so its integral is just t times that, and then plus the constant of integration. And for reasons you'll see in a second, I'm going to write that constant as the natural log of another constant. Right? So, but this is still a constant. If a is a constant, then the natural log of a is still a constant. All right, now if I rearrange this a little bit, right, use the property of logs actually. So if I subtract the natural log of a to the other side and use the property of the natural log, then I've got the natural log of V over A, right? Now, I'm actually going to drop the absolute value. The absolute value is just more of a formality. I've got the natural log of V over A equals negative t over RC, right? And again, I'm trying to solve for V. So now, how do I get rid of the natural log? Well, I raise each side of the equation to the exponent, right? So over here on the left, I'm left with V over A when I do that. And over here on the right, I've got e to the negative t over RC. Right? And now, to solve for V, this means that V is A, this constant, times e to the negative t over RC. Now we're not quite done yet. We need to figure out what is this constant. Well, remember, our initial condition was that at time 0 we had a voltage V0. So if I plug in 0 for this function of time, e to the 0 is 1 and I'm left with a. That must agree with our initial condition V0. So now I've solved the differential equation. The voltage across that capacitor is V equals the initial value times e to the negative t over RC. Okay, this is the solution. Well, there's a lot that we can say actually about this. Let's start by looking at a plot of this guy. So here's time axis, here's the voltage across the capacitor, which is also the voltage across the resistor, by the way, because there are only 2 nodes there. So this thing starts, as we said, at V0, and it comes down exponentially, and it asymptotically approaches 0. Now, this product of R and C comes up so frequently that it actually has its own name, right, and its own symbol. But first of all, let's look at the units of R and C. Right? Well, we know, so over here on the side, I'll do this in green. So R times C units. Right? Well, we know that resistor is ohms, right? But from Ohm's law, that's V over I. Right? So the units of an ohm is a volt divided by an amp. Okay, and an amp was a rate of change in charge. So an amp was a coulomb per second. All right, so this is actually seconds, volts per coulomb. Right? That's R in fundamental units there. Now, C, capacitance, well, we know this equation here. So C, if I solve for C, that is a charge, which is coulombs, divided by a volt. Excuse me, no, this is not correct. CV, there should be no squared there. Change your notes. This should not be a square. This is just C times V. So the units of C is a coulomb divided by a volt. So when we take R times C, okay, the units, you'll see we've got the seconds, the volts, over the coulombs, that's R, times the coulombs over the volts. And so the coulombs cancel, the volts cancel, and the product of R with C is actually seconds. Time. So this product, we call this the time constant of the circuit. And we give it the Greek letter tau. This is the time constant. All right, so go back to the plot in red. Notice something peculiar here is that the voltage across the capacitor never gets to 0. Okay, it gets closer and closer and closer to 0, but it never gets to 0. So you can't ask the question, how long does it take to get to 0? Right? Because it never does. Instead, you can ask, well, how long does it take to get to 1/2 of the voltage it started with, or 1/3 of the voltage it started with? This is similar to half-life in nuclear materials. They decay exponentially like this, and you can't talk about the life of the nuclear material because it's always there. The radiation is always there. But you can talk about how long does it take to decay half of what it started with. All right? But in circuits, we don't talk about half-life. We speak in terms of circuit time constants. How long does it take, okay, to get to approximately 37% of what you started with? So this is 37% of V0. How long is this time? Well, this is actually one time constant. Okay, the 37% comes from the following. Here's our voltage as a function of time. If I plug in a time constant, this is V0 times e to the negative RC over RC, right? Or V0 times e to the negative 1. E to the negative 1 is approximately, it's an irrational number, but it's approximately 0.37. Okay, or 37% of V0. So the takeaway here is that after one time constant, you have 37% of the voltage that you started with. After two time constants, e to the negative 2 is 0.135. So you have roughly 13.5% of the voltage that you started with. After 5 time constants, 5 time constants is approximately 0.67%. It's very small. Okay, you just take a look at this graph. If this is 1 time constant, 2 time constants puts us here, 3, 5 is off the graph somewhere over here. So you can see how small that graph would be. At this point we say, well, this is approximately 0. That after 5 time constants, if we allow 5 time constants to elapse, the capacitor, we say, has fully discharged its voltage. It's gone. Okay? It's completely gone. No voltage is there. Why this is important is because, well, this is no longer a DC circuit. Okay? A DC circuit is one whose voltage does not change, or current does not change. Okay, but the voltage is changing, right? This is not a DC circuit until 5 time constants has elapsed, when we say the voltage is approximately 0. That is when we have a DC circuit. So we say that this first order circuit, the source-free RC circuit, reaches DC steady state at 5 time constants. Now recall, and I have it written here, that the voltage is related to the charge stored in the capacitor, but also the energy that the capacitor is storing. So, as the voltage decays to 0, so does the charge on the capacitor plates, but more importantly, so does the energy that the capacitor is storing. It decays to 0 as well. Where is that energy going? Well, physically what's happening is, remember, the capacitor had initial energy, then it's supplying current to the resistor. The resistor is the other piece of this. The resistor is absorbing that energy as power, right? It's absorbing the energy, and that energy goes into, well, if it's a component resistor, it goes into heat, or if it's a physical thing like a toaster or a microwave or a light bulb, or maybe it's pushing something, right, mechanical. It's doing some sort of work, right? So that energy is doing some work there. Well, how much energy is this resistor absorbing? So let's take a look at that now. How much energy? Is the resistor absorbing? Well, we don't know an equation of the energy in a resistor, okay, but we do know the power in a resistor. The power is V squared over R, and we have the voltage across the resistor, right? It's this in the box. So the power in that resistor is V0 e to the minus t over RC squared divided by R. So when you square an exponential, right, that's twice the power of the exponential. So here is a function of time, of course. So you tell me what time it is, right? You tell me how much time has elapsed since the beginning of this experiment, right? And I will tell you how much power that resistor is currently absorbing. Now, the energy in the resistor is related to the power in that it's, again, a running integral. So the initial time here was 0, so we're going to integrate from 0 to whatever time we're interested in, t, v0 squared over r, e to the minus 2, and we're going to use a dummy variable of integration. So we can choose whatever we want. In the past we chose actually tau, but this might not be a good choice anymore because tau now means RC. So I'm going to choose a different variable of integration. Let's say S. This is a dummy variable of integration. It goes away once we integrate it. So the V0 squared and the R are constants. They can come out of the integral. And so I have this. So I need to integrate that guy, and the integral of that is negative RC over 2, right, e to the minus 2s over RC from 0 to t. And if you want to check, you can work backwards. You take the derivative of this thing, and you should get back the integrand. So if you take the derivative from the chain rule, you need to multiply by minus 2 over RC. So that minus 2 over RC cancels with this minus RC over 2. And we're left with the integrand again. So notice the r's here cancel. So we have negative v0 squared c over 2 times, now, I plug in t, I get e to the minus 2t. See, the s went away. Minus, I plug in 0 for s, and I get 1. Now the minuses, I've got a minus out here, so that can flip if we distribute it in. And let me write it like this: 1/2 C V0 squared times 1 minus e to the negative 2t over RC. All right? So this is the energy, again, absorbed by the resistor. You tell me what time, or how much time has elapsed since we let this thing go, right? And I'll tell you how much energy in total, right? In total, because we integrated from that point in time to right now. So we accumulated all of that energy, and I will tell you then how much energy the resistor has absorbed in total. The nice thing about this, look at and notice this, as we take the limit when t goes to infinity, okay, WR, so the total. So as we let this thing go now, for as long as we want, how much total energy has the resistor absorbed? Well, our t is here, our only t is there. E to the minus infinity is 0, right? That should be clear. So we have 1 in the parentheses, and so this thing approaches 1/2 C V0 squared. Well, why is that interesting? Here, that was this thing, which we said was the initial energy stored by the capacitor. So what we're saying here now is that that initial energy stored in the capacitor, if we wait long enough, gets absorbed by the resistor. And then poof, it's all gone, and the voltage is approximately 0, right? And at infinity, the voltage is 0. And now this circuit has reached its DC steady state. There's 0 current, and that's not changing. And there's 0 voltage, that is not changing. All right, let's look at another example. All right, suppose I have a 5 ohm resistor, a 0.1 farad capacitor, an 8 ohm resistor here, and a 12 ohm resistor on the right. And let's call this voltage here Vx. And let's call this voltage, of course, Vc. And we'll call this current Ix. And let us suppose, let's let the initial voltage on the capacitor, so at time t equals 0, is 15 volts. So again, I want to emphasize here that that had to have come from some voltage source, like a battery. We connected the capacitor to a battery of 15 volts, and then we disconnected the battery. Okay, and so it's originally charged. Find Vc, Vx, and Ix for time greater than 0. So it was initially 15 volts. Now what happens after that point in time to these quantities? The capacitor voltage, this resistor voltage, and this resistor's current. Notice there's no source in this circuit. The capacitor serves as the source, is the energy source for all of these things. All right, well, the trick here is to put the circuit in in the form of the previous example. All right, so let us do that. We've got the 8 ohm resistor in series with the 12 ohm. And then that combination, so that makes 20. And that combination is in parallel with the 5 ohm. So that combination makes 4. 4 ohm resistor and the 0.1 farad capacitor. And this is still VC. Now in doing that combination, we lost IX, because IX was the current through the 8 and the 12, not the 5, and we combined those things with the 5. So we lost IX, and we also lost VX, because VX was the voltage across the 12, and we combined that with the 8 and so forth. So but we still have VC, that's the voltage across the capacitor. Now, let's start by finding the time constant. All right. Well, once we put it in this form, the time constant should be straightforward. Time constant is R times C. Right? In the original circuit, it's not as straightforward. C is, 0.1 farad, right? But what is R? Is it 8? Is it 12? Is it 5? Well, neither. The R is actually the resistance that the capacitor sees at its terminals. So if you like, we can talk about Thevenin resistance. Remove the capacitor and find the equivalent resistance at its terminals. Well, since we put it in this form, clearly that's 4 ohms. So our time constant is 4 ohms times 0.1 farads, and that's equal to 0.4, and the units were, of course, seconds. Good. Now we need the function itself. So we just saw in the previous example that our function of time was the initial voltage, 15, times e to the minus t over RC, the time constant, and the time constant is 0.4. And then the units of this is volts. Okay, so that's part of our answer. Find VC for time greater than 0. Here it is. You tell me how much time has elapsed since our reference, and our reference is time equals 0. So you tell me what t is, and I'll tell you the voltage across the capacitor, and yet it's decaying exponentially. All right, so that should be straightforward from the previous example, but the new part here in this example is how do we get Vx and how do we get Ix? Well, notice now with Vc, we know the voltage across this series combination. So if we wanted the voltage across the 12 ohm resistor, we can use voltage division in this problem. Vx of t equals the voltage across the series combination, which is Vc, times the resistor whose voltage we want, 12 ohms, divided by the sum of the two series resistors. So this fraction, this is 12 over 20, so there's a 4 there, that's 3/5. 3/5 times 15 is 9. So this is 9 e to the minus t over 0.4 volts. Good. So we have the voltage across this resistor. To get the current through that resistor, we can use good old Ohm's law. I is V over R, so in this case that's Vx of t over 12 ohms, right? So if I plug in Vx, I've got the 9 over the 12, so 9 volts over 12 ohms. That is 3/4 amps. And then I still have that e to the negative t over 0.4. And we're done with this example. All right, let's look at another example, that one that highlights how exactly the capacitor is getting its energy. So I want to show you something that's more indicative of what you would see in practice. Right, suppose now we have this 20 volt source. And connected to it is a 3 ohm resistor. And we're going to put a switch here. And we're going to switch at t equals 0 again. Put 9 ohms here, and 1 ohm here, and a capacitor of 20 millifarads. And we're interested again in the voltage across that capacitor, call it V. Right, and the goal here of this problem is to find V of t, the capacitor voltage, for time t greater than 0. Okay? In other words, after the switch. So the switch is closed initially, and then at t equals 0, we open the switch and let this thing run. Okay? So before the switch, we have the following circuit. Actually, I'm not going to draw it again. I'll just come up here. Before the switch, we've got this circuit. Okay? What's the capacitor voltage? Well, this is a DC circuit. So this is now a problem from 2 videos ago. Let's replace the capacitor with its DC equivalence. Like this. Right? So before the switch, okay, we'll call this V of 0 minus, meaning just before the switch happens at 0, t equals 0. So this voltage now we have to get. All right, we'll observe that no current goes through this 1 ohm resistor because it has no return path. So there's no drop across that resistor. Instead, let's find the drop here. Call that Vx. The drop across Vx is equal to, we have a series circuit now, effectively, because no current goes through the 1. So we can use voltage division. Right? So this fraction is 9/12 or 3/4. 3/4 of 20 is 15. So Vx is 15. That's the voltage at this node up top with respect to this node on the bottom. But there's no drop across the 1 ohm resistor. So if there's no drop from left to right, that's also the voltage from this node, and it just circled, with respect to the bottom. That's precisely the voltage we're looking for. Right? So you see, it's this voltage source that's giving the initial charge to the capacitor. Then, when we first started talking about capacitors, we said that the voltage across a capacitor cannot change abruptly. So, just after the switch, must be the voltage just before the switch, which is 15 volts. This is our initial value. Okay, now that we've got how many volts the capacitor starts with, now let's consider after the switch. So I'm going to come up here to my original figure, and I'm going to open this guy, right? Well, now, because of this switch is open, there's no return path for this current here. So there is no current here. And so the only place we have current is this loop on the right. Observe this is a source-free RC circuit. So let's put it in the form that we're used to seeing. Right? We've got 20 millifarads and 10 ohms. So the circuit time constant is 10 ohms times 20 millifarads, or if you like, 20 times 10 to the minus third farads. Okay, so 10 times 20 is 200, or 2 times 10 to the second, times 10 to the minus 3 gives us 0.2 seconds. Now, we have the time constant, we have the initial voltage, so the voltage across that capacitor as a function of time is 15 e to the minus t over 0.2 volts. And this is again for t greater than 0. Now, for the RL circuit, let's once again assume that the inductor this time is charged. I guess we'll say it's initially storing energy. So here's L, here's R, right? And we'll look at the voltage. Call the voltage here, just to match your book, VL. So we're looking at that voltage, and this voltage we'll call VR. And of course there is a common current here. So this problem is the dual to the first problem where there was a common voltage and we had two currents. It's the dual to the first problem we looked at, the very first one. Now, let us assume, again, that at some reference point, we're going to call that reference point 0, time equals 0. We're going to say that I, the current, was not 0, it was some initial current. Okay, so at some point there was this current that was going through the inductor. All right, well, I do want to remind you then that the initial energy then in the inductor is 1/2 L times that initial current squared. Now if we go around the loop and we do a KVL equation, we see that VL plus VR equals 0, right? So you go around the loop, VR drops, then VL drops, and you're back to where you started. But we know what VL is in an inductor. It's L di dt. So we'll write L times di dt. And we know what R is across a resistor. It's I times R. And again, this is a first-order differential equation, which makes this circuit then a first-order circuit. So we need to solve that differential equation. We need to solve it for I. So again, we can use the method of separation of variables. So let's get all of the i's on one side, 1 over I di, and then we'll get negative 1 over L, excuse me. So if we move the if we move the R over, right, we get 1 over R, or excuse me, negative R over L dt. All right, so now let's integrate, and we get the natural log of I equals, well, this is negative R over L times T plus the initial current, right, or excuse me, plus the constant of integration. So we'll write the constant of integration as A. We'll write it as the natural log of A. So this is a constant. If A is a constant, then the natural log is a constant. So let's subtract over the constant and use a property of natural logs there. All right. Raise both sides to the e power, so this gives me I over A equals e to the negative R over L times T. Then move the A to the other side. A times e to the negative R over L T. All right, and we need to figure out what this constant should be. But our initial condition was that at time equals 0, we have I0. So if I plug in t equals 0 here, I better get I0. So I of 0 is equal to A, right? Because e to the 0 is 1, and that should give me I0. So A must be I0. So we've got this. Times T. Now, if we put it in a little bit different form, and actually we want to match the form from the LC circuit, or excuse me, from the RC circuit. We're going to match the form where we had V0 e to the negative t over tau. Right? Well, let's do that. Let's say I equals I0 e to the negative t over L over R, right? L over R. Then the time constant for the RL circuit is this L over R, right? And let's just check the units on that guy. I'll do that over here. The units of L over R. So for L, you know that there's the equation V equals L di dt. So voltage equals henries, and di dt, that's a change in charge, coulombs, over a change in time, seconds. So the L, the Henry, is actually seconds times volts over coulombs. Excuse me. This is L di dt, di. So a change in not charge, but a change in amps. This is amps over here. So this is not charge. This is amps. All right. Then resistor, you know, of course, this is V over amps. So when I take L over R, the units there, seconds, volts over amps, divided by volts over amps, or multiplied by the reciprocal, amps over volts, amps cancel, volts cancel, and again, wonderfully, I get seconds time. So the time constant for the RL circuit is L over R, and that unit is seconds. Great. So our equation then for the current in that inductor is right here. So let's make a plot of it. And again, the initial condition, I0, and then it decays to 0. Now this looks very similar to the RC circuit, and it is. Everything that we said about the RC circuit applies here. For example, after one time constant, so if we plug in L over R into T, we get I0 e to the negative 1, and that's approximately 37% of the initial condition. So after one time constant, we're about right here, 37%. And after 5 time constants, we say that I is approximately 0, and the circuit is at its DC steady state. Also, just like the RC circuit, remember the energy is related to the current. Okay, the energy in the inductor is related to the current squared. Okay, so as the current goes down, decays to 0, so does the energy stored in the inductor's magnetic field. Where does that energy go? It's dissipated in the resistor. right, via heat or work or something like that. Right, so let's find out how much energy we have. Well, in a resistor, so this will be the energy total energy. Total energy absorbed by the resistor. Right? Well, the power absorbed by the resistor we can write as I squared R. And we just found out then that's going to be I0 e to the minus t over tau squared times R. And if I bring in that square, this is I0 squared R e to the minus t over e to the minus 2t e to the minus 2t over tau watts. Right? If I want the energy absorbed by that resistor, then I need to integrate from our reference point, which was t equals 0, to the time right now. 0 squared, I0 squared R, e to the negative 2, and we'll change this to s, ds. S is the dummy variable of integration. So I move that out, the constants, integrate. Right, so I need a tau, I need a negative over 2s, e to the, not 2s, excuse me, just 2, e to the negative 2s over tau, from 0 to t. Then, if I plug in t, okay, I have e to the negative 2t over tau, so the s's go away, the dummy variable. And I plug in 0 in for s. Like this. Tau, remember, is L over R. So one of those, that R cancels with this R, and I get L over 2 e to the negative 2t over tau minus 1. And if I distribute the negative inside, and I rearrange this a little bit, I get this. This is the energy, the total energy at time t that the resistor has absorbed. So as I let time go on, this goes to 0, and I get 1/2 L I0 squared. That's exactly the energy that the inductor started with. Now, I do want to bring up a point here. If we were to increase the time constant, and I'll draw that in blue, if we increase the time constant either by raising L or lowering R, by definition then, it takes longer for the energy or the current to dissipate. So this would correspond to a larger time constant. It takes longer. And a shorter time constant, of course, could look like this. This would be a shorter time constant. Smaller time constant, that is. Okay, so let's look at an example. Suppose we have a 40-volt source, and that's connected to a 2-ohm resistor, and there's a switch here that is opened at time t equals 0, our reference point in time. And this is a 2 Henry inductor, and we are interested in the current traveling through that inductor, call that I of t. So we're going to say find I of t for time greater than 0. Okay, so this would be this whole switch thing would be the situation if you had a circuit and you had the 40 volts connected, and then you turned off this part of the circuit. You just hit a switch and you turn it off. So before you turned it off, current was going through that inductor. After you turn it off and after you wait for a while, of course there's no source here, so when you wait for a while there will be 0 current. But the current through an inductor cannot change instantaneously. So how does that change from we had a non-zero current to we have a 0 current? It cannot happen instantaneously. Now the first thing we have to do is find how much current was traveling through this inductor before the switch, right? In other words, what is the initial value of that current once it starts to dissipate? All right, well, before the switch, then, so I'll close the switch up here. This is a DC circuit. Okay, it's been sitting around for a while. Everything's reached its steady state, right? And so let's calculate the current right before the switch. So this is I0 minus. All right, well, before the switch, the inductor then, since this is at its steady state, DC equivalent of the inductor is a short circuit. All right. So I have this circuit, and here is I0 minus, right, that we need to calculate. So again, I replaced, this is the last video's concept, I replaced the inductor with its DC equivalent, which is a short circuit. Now observe that the 6 ohm resistor is shorted out. It has 0 potential difference across it. So this is also I0 minus, because all of this current is going to go this way. None of it can go through here because it's shorted out. All right, so I need to find that current, right? So effectively, this 16 ohm resistor is not there. It has no effect because it's shorted out. So notice the 12 and the 4 are in parallel. The 12 and the 4 ohm resistors are in parallel. They are both connected to this node and this node. So they're in parallel, they make 3. 3 ohms then is in series with the 2 ohms, because all of the current that goes to the 2 ohms must go through either the 12 or the 4. So we have 3 ohms in parallel with 5 ohms, or excuse me, 3 ohms in parallel with 2 ohms, that makes 5 ohms. So the current here, we have 40 volts, that sees 5 ohms. So the current here is 8 amps. So 8 amps approaches now this parallel combination, the 12 and the 4. We want to know how much current goes through the 4. So we can get that using current division. I of 0 minus equals the 8 amps. How does the 8 amps split? Well, we'll take the resistor whose current we're not interested in and divide it by the 4 ohm and the 12 ohm. So this fraction is 12 over 16, or 3/4. 3/4 of 8 is 6 amps. Right. There's our initial current. Now come back up here to the original circuit. After the switch, this is an open circuit, right? Because the switch was right there. So this is open, so the source has been switched out. So has this 2 ohm resistor. It's been switched out. So eventually this current dies to 0. Okay. But how does it die to 0? Let's find the time constant and observe that the 4 ohm resistor is now in series with this 12 ohm resistor, making 16. And that equivalent 16 is in parallel with this 16. So that makes 8. So the time constant clearly is L over R. That's 2 Henry over 8 ohms. So that's 1/4 seconds. I'll write it in decimal form, 0.25 seconds. All right, so we have the initial value. We have the time constant. So we know then I of t is going to follow this form where it's the initial value, e to the minus t over tau, 0.25. And this is amps. And again, this is for t greater than 0. That's the answer. It can be a little tricky if you're not quite used to it. Let's do one more. All right, so let's say now we have a current source, and we'll call that 15 amps. And in parallel with that is a 24 ohm resistor. Okay, and there's a switch, and it was closed and it switched open at our reference point t equals 0. And then we'll have a 12 ohm resistor, 5 ohm resistor, and here is our inductor of 2 Henry. And an 8 ohm resistor here. Okay, and the current we're looking for is the inductor current, I of t. All right, so we're going to find I of t for time greater than 0. Okay, first thing we need to do is find the initial value. So when the switch is closed, okay, right before it's opened, so I'll just write this as a closed, and we're going to find the current right before the switch. All right, well, right before the switch, assuming the circuit has been built and it's been sitting around for a little bit, then the circuit has reached its DC steady state equivalent, meaning the inductor can be modeled or replaced with a short circuit. Right? We need to find this current here, I of 0 minus. All right, well, notice again, just like the previous example, the 5 ohm resistor is shorted out. Okay, so no current goes this way, 0. 0 current travels that way. So all we need to do is find how much current goes through the 12 ohm resistor, because all of the current through the 12 ohm, I'll do this in red, all of the current through the 12 ohm resistor must go through this way then, I0 minus. So I0 minus is also right there, because nothing comes this way. Alright, also notice then that the 24 ohm resistor is in parallel with the 8 ohm resistor. That's because they're both connected to this node up top and this node down here. Okay, the 24 and the 8 make 6 ohms. So let me redraw this now. 6 ohms. This is essentially what we have now, for the reasons why that were just stated. Okay, we need to find I0 minus. We can do this with current division because the 12 ohm and the 6 ohm are in parallel. So I0 minus is 15 amps times the resistor whose current we're not interested in, 6 ohms, divided by the sum of the two. Okay, so this fraction is 1/3. 1/3 of 15 is 5 amps. That's our initial condition because I0 minus, the current right before the switch through the inductor, must be the current right after the switch through the inductor, because the current can't change abruptly. So right after the switch, we know that the current is 5 amps. Now the question is, how fast does it decay to 0? That is, what is the time constant? All right, well, in the original circuit, the switch was right here. So let's open that switch now, because we're talking after the switch. Well, the 8, let's identify the nodes. Can we combine anything? Here are the nodes of the circuit. No current goes this way because it has no return path. The 12 and the 8 are in series now because this is open. So that makes 20, and that 20 is in parallel with the 5, so that makes 4. So we can redraw the right part of this circuit like this. Okay, now it should be clear that the time constant is 2 Henry over 4 ohms, or 0.5 seconds. Now, the solution then is that the current at any time after the switch is 5, the initial condition, times e to the negative t over tau. Tau is 0.5 amps. So that's all there is to it. Whether you're dealing with the RC circuit or the RL circuit, you want to first find the initial voltage if it's RC circuit, or current if it's an RL circuit. Second, find the time constant. Third, write down the equation. Because you know the form of the solution. We solved the differential equation. We did all the heavy lifting. And we know that the form of the equation is this decaying exponential. Now, I do want to bring up I think it was two videos ago, when we first started discussing the capacitor. I showed you, I demonstrated to you the two circuits. One had the capacitor and one did not. And we turned off the lights and observed that the circuit with the capacitor, the light took some time to fade. Right? Now, after this lesson, 13, you should be at least starting to understand why the circuit with the capacitor is such that the light fades slowly. The capacitor is preventing the energy from just instantaneously being dissipated through the light and through the resistor. Okay, it's slowing that process down a little bit.